After AND, we get to the OR instruction, and a similar hardware would be used, with the difference that instead of the AND gate, it would use the OR gate. Here you could see how we again bring up the 8-bit A and 8-bit B here. The corresponding bits would be this time OR, and this would be out 0 to out 7. So the abstraction would be that we have an 8-bit OR, one 8-bit A and another 8-bit B, both inputs of the OR or 8-bit ORer, and the output would be out. So again, all the instructions that have been implemented in the AT85 suggest that one of the inputs is always the A register. The other inputs could be from any one of the 7 8-bit registers and also one memory location, and the result would be also saved in the A register, and the corresponding instructions are again a lot like the previous one, or A with A, B, C, D, E, H, L, and M. This just means that or A means again one of the inputs is A. It could be ORed with all of the 7 8-bit registers, and M also we have ORI byte. This means that we could provide an immediate value. This I means immediate. You see, this is or A means that one of the inputs is always A, or I also means that one of the inputs is always A and the destination is also A, but the other input, instead of providing it as one of the registers, it could be provided directly as an immediate value. The opcodes for the OR would be equal to 10110, and one of the 8 values here would specify if this is one of the 7 registers called B, C, D, E, H, L, and A, or it is a memory location called M, which its value is 110. Again, if it is, as an example, if we have B6 in the IR register in hex or in binary, we have 1011. You see, when I say B6 in hex, it is just like when I say ORA with M. It is for us to communicate better. In the computer, in the IR register, it would have 10110110, and again, this would be another abstraction. You know that everything would be at the transistor level and different wires, that everything has been explained. If you want to go more down, it has been explained in my other course. But here, if we have this value in the IR register, what AT85 microprocessor does is that it would look at the HL register pair, would choose the location that this is pointing to, and would bring that 8-bit value, put it in the one of the inputs of the 8-bit order, and would load the other input with the contents of the accumulator, and the result would be saved again in the same A register. So as an example, let's imagine that we had 10110, or this is 1, I think, if I look at the opcodes again. So we said that the opcode in binary is B, right? 1011 means B. So let's say that we had 10110,000, that the user, you as the programmer, you have put this value in a location in memory. It has been fetched in the AT85 microprocessor. It is now in the IR register. What the CPU would do is that it would just load one of the inputs with the contents of the B register. Let's imagine that it is 17H, which in binary it would be this, and load the other input of the 8-bit order with the contents in the A register, which is B6 in hex or 1011,011 in hex in binary. So based on this truth table, it would be 0 and 1. It is 1, 1 and 1 is 1, 1 and 1 is 1, 0, 0, 1 and 1, 1, 0, 1. What is this? This would be 8 plus 2, 11. This would be B, and this would be 7. So the result is equal to B7, and this would be put inside the A register. And finally, we want to implement the other one, which is XOR. After and OR, we get to the XOR. Again, the same thing. Instead of OR and AND, we use the XOR gate, which we have explained about the truth table, that the output is 0 when both inputs are equal. We could create this abstraction. Again, one of the inputs is always A register. The output is also always A register. The other input could come from any one of the 7 registers or a location in M, which the HL register pair is pointing to. Now, for this, the opcode is equal to well, this would be actually A8 to AF. So this would be A8, A9, AA, A, B, C, D, E, and F. If you look, we have 10101. This would be the opcode of XRA, and the other 3 bits would specify the other operand. So if you convert this binary to hex, you see that these are the hexadecimal equivalent of the bit pattern related to the XRA, which is for XOR based on the truth table that we showed. We also have XRI, which would be, well, actually, I'm not sure if we have, let me just check a moment. Well, yes, actually, we would have XRI and byte as the immediate XOR, which means that the value, the byte would be provided directly as one of the operands. The other operand would always come from the A or the A register. Now, well, yes, actually, we had the XR byte here. Let's imagine that we have this value. Actually, I want to make 2 examples. One of them is that, well, we had the value of A8 or 10101000. This would be in the IR register. So the steps that the 8085 microprocessor would take to execute this would be to load the B contents in one of the inputs of the XOR gate that we said. This is the abstraction that we actually use. The same thing, just this would be the 8-bit XOR, and the other input would come from the A register. Based on this truth table, the XOR would be done. 0 and 1 would be 1, 0, 0, 0. The equal would be equal to 0, right? 1 and 1 is 0. 1 and 0 is 1. 0 and 0 is 0. 1 and 0 is 1. What is this? Well, this is A and this is 1. A1 would be the new value loaded inside the A register. Another example is this. Now let's say actually exactly after this instruction we have the XRI byte, which I think the value would be EE. The opcode for XRI would be EE. So we had, let's say that we had EE B6. This means that this instruction means that I want the contents of the A register to be XOR with the B6 value. So the A register is already equal to A1. A1 in the binary is 1010 and 1 is 0001, and B6 is equal to 1011 and 6 is 0110. I hope this makes sense. You see, as the programmer, let's say that this was your RAM or read-only memory. And what you did is that first you put the value of 1010 1000, and this was the address of 0. This is the 1, 2, 3, and so on. And in the next place, you have put the value of EE. E is the 1110 1110, and then B6, which would be 10110110, or like this was another value. What I mean is that as the programmer, you have written this in the RAM first, the first value, the first instruction, and the PC value has been equal to 0. The CPU has been reset. So the first instruction, which is this, has been brought inside the IR register. The 8085 has executed this instruction. Therefore, the A accumulator has been equal to A1. Then the second instruction would be brought inside the 8085 microprocessor. It finds out that it would have an operand equal to B6 or this value in the binary. But it also knows that, how does it know that? Because the instruction, this pattern, zeros and ones pattern, suggests that this is a 2-byte instruction. 1 byte, the first byte is the opcode, the second byte, the opcode for the XOR I, and the other byte is the data, the immediate value that should be inserted in one of the inputs of our 8-bit XOR. So this is the value of the A register, and this is the value provided as part of the instruction of XRI byte. XOR would be done based on the truth table that we explained. 1 0 would be 1 0 1 1 0 1 1 0 0 0 0 1 they are different. 1 1 1 they are the same. 0 0 0 they are the same. Zeros 1 1 they are the same. 0, this is 1, this is 7. So now A register is equal to 7. You see, A register just gets manipulated and changed based on all the instruction that the programmer is just using. How this pattern of zeros and ones, how does 8085 microprocessor knows what to do with these zeros and ones? We know that there is a control unit as the brain of the 8085 microprocessor, which there would be a read-only memory acting as a table. The 8085 would look up the pattern of the instruction into that table, and the corresponding signals would be issued. The corresponding steps that we just explained would be issued for the corresponding hardware, and we would see the result as follows. So far we've been able to understand about 27 different instructions, how these 27 instructions relate to the AND, to OR, and also XOR logical operations.